In the previous lesson, you learned about the components that make up an electrochemical battery cell. You saw in a fairly abstract way how electrons move when the cell is charged and when it's discharged, but I didn't really explain why electrons move, and in this lecture topic I hope to talk a little bit more about that in detail. To understand how electrochemical cells store and release energy, we need to discuss the idea of potential energy. The picture of a skateboarder on this slide illustrates this idea of potential energy using a concept that we are all much more familiar with. We're all more familiar with gravitational potential energy and maybe not so familiar with electrochemical potential energy, but it really turns out that they're the same idea but just from different branches of physics. So if we think about this skateboarder on this skateboard ramp that's shaped a little bit like a parabola, we know that if the skateboarder is either at the top on one side or of the other side of the ramp, gravity wants to pull him downward. So if the skateboarder is stationary at either one of these two top positions, he has some potential energy that could be released to make him move. And we know that if the skateboarder is in the center position at the bottom of this ramp, that gravity is still trying to pull him downward, but there's no way on the ramp for him to go in a downward direction, so he will not be able to move. We can understand electrochemical cells in a similar way. Electrochemical potential energy can be stored in a battery cell just like gravitational potential energy is stored by the skateboarder at the top of the ramp. When we charge a battery cell, we're bringing it up to a higher state of potential energy. And when we discharge a battery cell, we're bringing it to a lower state of potential energy. And when the cell is fully discharged, it is at the lowest state of potential energy that it can be at, and it cannot be discharged any further, which is like the skateboarder at the bottom of the ramp. I bring back this cross-section illustration of a battery cell from a previous lesson to illustrate the discharge process. A charged battery cell holds electrochemical potential energy, and this potential energy at the negative electrode favors a chemical process that releases electrons into the external circuit and releases positively charged cations into the electrolyte. This is just the same idea as the skateboarder on the top of the ramp. Gravitational potential energy favors a process whereby the skateboarder would move down the ramp. So if the skateboarder may be stuck at the top of the ramp because of friction, and that friction is removed, then we know the skateboarder will start accelerating down the ramp toward the bottom. So in the same way, this electrochemical potential energy in the negative electrode is stuck inside the battery cell until an electronic circuit exterior to the battery cell is completed. You see, there's an electrical friction or a resistance that prohibits electron movement until the circuit is completed. But once the external circuit is completed, it's possible to release this electrochemical potential energy from the negative electrode by producing these electrons that go into the negative terminal of the battery and into the circuit, and also by producing positively charged cations that go into the electrolyte. In a similar way, the positive electrode stores up electrochemical potential energy, but in this case the potential energy favors a different chemical process whereby it accepts electrons from the external circuit and accepts positively charged cations from the electrolyte in order to reduce its potential energy. And again, it's only when the circuit external to the battery is completed that the resistance that prohibits this energy from being turned into useful electrical energy is removed. And it's the combination of the potential energy stored in the negative electrode and the positive electrode together with this external circuit that makes this entire discharge process possible. Now, while the circuit exterior to the cell is not complete, there's still an electrical pressure that has built up because of this electrochemical potential energy that wants to be released to do work. And this electrical pressure is called electrical potential. There's a potential energy stored in the cell that causes the electrical potential difference between one electrode and the other. And this potential difference is actually something that can be measured with a voltmeter, and it's called the cell voltage. When the external circuit is completed and electrons are free to flow from the negative electrode through the circuit to the positive electrode, then work can be done in the external circuit. And what happens is that this electrochemical potential energy is converted into electrical energy. Again, if you think back to the example of the skateboarder, in that case, gravitational potential energy was converted into kinetic energy as the skateboarder started moving. Work was done on the skateboarder by bringing the skateboarder from zero velocity up to some positive velocity as he went down the ramp. So while the process that occurs in a battery cell is an electrochemical process, and the process that occurs with the skateboarder is a mechanical process, a lot of the same ideas apply, and I believe it can be helpful to have this skateboarder image in your mind when you're thinking about how a battery cell works. So what about rechargeable cells? Remember that we've talked about two different categories of battery cells, primary cells and secondary cells. Primary cells are not rechargeable. The electrochemical reaction that occurs during discharge of a primary cell is not reversible. During discharge, the chemical compounds are changed permanently, and so the electrochemical potential energy is released until the original compounds are completely exhausted. And even if I try to recharge a primary battery, the compounds that have been formed during discharge will not recombine into the original compounds that were present before the discharge, and therefore it will not recharge the battery cell. And this is the principal reason that primary cells can be used only one time. Secondary or rechargeable battery cells, on the other hand, are special in the sense that their chemical reaction has been designed or chosen in such a way that it is completely reversible. The original chemical compounds that changed when we discharge the battery cells can actually be reconstituted in their original form by the application of an external potential between the electrodes that injects energy into the cell. Ideally, these secondary battery cells can be discharged and recharged an infinite number of times, but we know from our own personal experience that this is not the case. So we ask, why? What is happening? And it turns out that the simple understanding we have at this point of how a battery cell discharges and recharges is true for the primary chemical reaction that's happening in the cell, but it neglects the fact that there are other chemical processes happening and mechanical processes happening inside the battery cell that cause degradation or aging of the cell. So that is, inside the battery cell there are multiple chemical processes happening where only one of them, hopefully the dominant one, is the electrochemical reaction that we want to happen that's releasing energy into the load circuit. The other unintended chemical reactions can be parasitic in nature and cause materials in the battery to degrade, and there could be also mechanical processes causing stresses and strains that cause the materials in the battery to degrade. So the life of a secondary battery cell is not primarily determined by its main chemical reaction. Rather, the life is determined by how quickly these other degradation processes occur. I bring back the same diagram of the cross-section of the battery cell to illustrate the charge process for a secondary cell. As you might imagine, it's exactly the opposite of the discharge process. During charge, the cations move from the positive to the negative electrodes through the electrolyte, and the electrons move from the positive to the negative electrode through the external circuit. This action happens in response to an externally applied voltage that is greater than the rest voltage at the terminals of a battery cell. Because this external voltage is higher than the cell voltage, that means that there's a greater potential energy exterior to the cell than there is interior to the cell, and so energy is pumped back into the cell, and it's that energy that transforms the active chemicals back to their original state. And it's a lot like the skateboarder. If he's at the bottom of the ramp, but you apply a force, you can push him back up the ramp. So if you apply energy to the skateboarder, you can, again, reconstitute him in a recharged state at the top of the ramp where he can go back down again at a later point in time. When we're charging the battery, we often have to be much more careful than when we are discharging the battery cell. Manufacturers publish safe operating voltage limits for their battery cells, If we overcharge a battery cell, we can be forcing energy into this cell that the cell is no longer able to accept in a safe way. And by doing that, we can cause irreversible damage to the cell and in some cases even fires or explosions. Also, the ability of a battery cell to sustain a high level of health when it is overcharged depends a lot on the chemistry of the battery cell. For example, lead-acid battery cells can be slowly overcharged with no permanent damage. What happens when we slowly overcharge a lead-acid battery cell is that water in the electrolyte dissociates into hydrogen and oxygen gases. And if that's done slowly enough, the hydrogen and oxygen gases will actually recombine back into water. And so there's this kind of a process happening at the top level of state of charge that if the battery cell is sealed and these gases do not escape, can actually happen quite safely, and it doesn't cause degradation of the battery cell. This process at the top of charge is called a float charge, and many lead-acid battery chargers are designed to have a float charge to maintain the battery at a top state of charge. This is not something you can do with a lithium-ion battery cell. If you overcharge a lithium-ion battery cell, it does not result in a chemical process happening that is reversible. Often the electrolyte will decompose just as with the lead-acid cell, but in this case it does not recombine. And when the electrolyte in a lithium-ion battery cell decomposes, it turns into gases that cause the cell to puff up, just like this picture on the slide of the mobile phone battery. And once the cell has puffed up like this, it cannot be returned to its previous state. The electrolyte is permanently damaged. The ionic resistance of the electrolyte is increased because there's less functional electrolyte present. The gases that are produced are often flammable and can cause fires and explosions. And so you must be really careful when charging a lithium-ion battery cell to ensure that you do so safely. And there are also voltage limits for how much we are permitted to discharge a battery cell, but the risks associated with over-discharge are much often less serious than the risks associated with overcharge. And so they are not safety risks as much as they are lifetime risks. For example, if you do not maintain a lead-acid battery cell at a high state of charge, what happens is that hard lead sulfate crystals will begin to form on the electrodes, and these crystals cannot be converted by a standard battery charger back into lead and sulfuric acid. In some cases, it is possible to recover these lead sulfate crystals using a specialized battery charger that uses voltage pulses to try to break up these crystals, but this is a specialized topic and it's not even guaranteed to work in general. So most lead-acid battery cells are used in applications that must maintain a high state of charge. For example, the automobile lead-acid battery really should never be discharged below about 80% state of charge. Otherwise, it will start to age quite rapidly because of the formation of these crystals. For some applications, there are specialized lead-acid battery cells called deep cycle battery cells that can be used over a wider range of state of charge, and usually this is accomplished simply by using thicker lead plates that just take longer to age before the battery cell is considered dead. I would like to take a couple of minutes to illustrate briefly how a battery cell is charged in a very common scenario. So on this page I have 4 different diagrams corresponding to different ways of looking at the same experiment, and that is charging a battery cell. In this case, the example is for a lithium-ion battery cell, which is being charged from a mid-level 50% state of charge up to a fully charged state, 100% state of charge. In the top left plot, I show you terminal voltage of the battery cell versus time as it's charged. On the top right, I show you state of charge versus time. On the bottom left, I show you electrical current versus time, and on the bottom right, I show you charging power versus time. In the convention that I'm using to describe electrical current and power, negative values correspond to charging and positive values correspond to discharging. And in this experiment, I'm showing 2 different charging modes. One is called constant current, constant voltage, and the other is called constant power, constant voltage. In constant current, constant voltage charging, you regulate the charging current at a constant value until the cell's measured terminal voltage reaches some maximum manufacturer specified value. And at that point in time, you switch from a constant current operational mode to a mode where you simply hold the voltage of the cell constant at that maximum value, and you wait until current decays to a very, very small absolute level. Constant power, constant voltage charging is similar, except during the first phase, we don't apply a constant electrical current to the cell, but instead we apply a constant charging power to the cell until a charging voltage limit is reached. And then in the second phase, again, you simply hold that voltage constant until the charging power decreases to a small number in magnitude. So looking at the bottom left picture, the solid blue line shows current versus time for the constant current, constant voltage charge scheme. You can see that current is being held constant at a 9 ampere level until the maximum voltage of 4.15 volts is attained. Then, when we hold the voltage at that level, the magnitude of current decreases towards zero until the battery cell is completely charged. If instead we do a constant power, constant voltage charging, we see that the current is slowly decreasing in magnitude during the constant power portion of the charge cycle, and that's shown by the green dashed line. And this is because power equals voltage times current. If power is constant and voltage is increasing, then current must be decreasing in magnitude. So now let's look at the bottom right picture, and we can examine the power versus time. And when we look at the constant power, constant voltage charging profile, we see that the dotted green line shows a constant power level for the first portion as expected, followed by decreasing levels of absolute power while we hold the voltage constant. And you can also see that if we're performing a constant current, constant voltage charging, that in fact during the first portion the magnitude of power is increasing because a constant current multiplied by an increasing voltage gives me an increasing absolute power. In the top right picture, you can see that during constant current, constant voltage charge, the blue line, that state of charge increases linearly over the first segment until it reaches the voltage limit, and after that the state of charge gradually tapers and approaches the 100% state of charge level. The constant power, constant voltage line has a similar behavior, except that it is not strictly linear change in state of charge in the first section, but it's pretty close. You may already know that many battery chargers can quite quickly charge a battery cell up to about 80% state of charge, and sometimes even 90% state of charge, but that it can take quite a while to charge the battery the remaining amount up to 100% state of charge. And now maybe you can see from these graphs why that might be the case. It's possible to charge a battery cell quite quickly at the beginning without violating this maximum voltage limit, but as soon as we hit that maximum voltage limit, we have to turn down the charge rate in order to protect the battery cell and therefore to protect the user also. And so the final 10% or 20% of the charge often takes as much time or nearly as much time as the first 80% of the charging period. Notice that on this slide I'm illustrating how we can charge an individual battery cell. When we're charging a battery pack that comprises multiple cells, there are some extra details that we'll need to be careful about. And we'll talk about those later on in this course when we look at requirements on a battery management system and how it manages the battery pack charger. Also, many of the details of why the battery cell responds exactly the way it responds in these pictures is something that's beyond the scope of what we can talk about at this point, but we will study those details in the second course of the specialization, and you will learn how to write Octave or MATLAB code to simulate and reproduce the results on this slide for yourself. And so to summarize this lecture topic, battery cells store energy as electrochemical potential energy. And whenever an external circuit is completed, this provides a pathway for that electrochemical potential energy to be converted into electrical energy. The negative electrode supplies electrons to the external circuit, and the positive electrode sinks electrons from the circuit, thus powering the load and discharging the battery cell. In a rechargeable or a secondary battery cell, whenever the charger provides electrical energy to the cell, That energy is stored as electrochemical potential energy again that can be used at a later date. When we charge a battery cell, we must be careful to maintain the cell within manufacturer-specified voltage limits to ensure safety and to ensure long life as long as possible. And there are two commonly used modalities for charging a battery cell, and these are known as constant current, constant voltage, and constant power, constant voltage.